Hi everyone, welcome to ECO730. So we are going to start with chapter 6. Earlier on, I actually did upload some readings for you to do, which is basically on data structures. This was basically to prepare you guys to just refresh on either your econometrics 3 or statistics. Just to remind you that we are going to deal with different data structures, and specifically for this semester, we are going to deal with the two types. Term 1, we will be dealing with cross-sectional data, and then term 2, we will be dealing with time series data. All right. So often when you pick up a paper or whatever the case is, you are you know, always curious about the functional form that is actually used in a particular paper or for a particular study. And in many cases, we are always, being told that, it's always very important or it's always very convenient to actually make use of logarithmic functional forms. And I mean, you have also covered this topic in Econometrics 3. So basically, we are going to zoom in as to why is it the case. It is the case because, first of all, when we are dealing with a logarithmic functional form, it makes things easier. For instance, it's easier to interpret because you can interpret it as an elasticity, and we know that elasticity is in percentages. Meaning that, for example, if you have variable x and y, where y is a dependent variable and x is an independent variable. So you can easily then interpret to say, well, if x increases by 1%, then y will increase by so and so percentages. So you can only do that mostly and conveniently when you are dealing with a logarithmic functional form. Secondly, when you have a logged function, then it's also easier to work with the values that you're working with in terms of the coefficients. Why? Because sometimes you are confronted with a situation whereby you are dealing with variables that are measured in different units. Some are in millions, some are in billions. Now, if you want some sort of uniformity, it's either you upscale the variables that are in millions or you downscale the variables that are in billions. Now, this will actually cause a mismatch. This rescaling will cause a mismatch because when you upscale a value that was in million to billion, you're actually overstating it. Whereas if you downscale the variable which was in billion to million to sort of seek some consistency, you are actually understating it. So therefore, when you convert the variables into logarithms, then you actually eliminate that problem of rescaling, and you can then go ahead and do the estimation. And then thirdly, sometimes you have extreme values, okay, whereby, for example, if you have a group of 4 people, maybe three of those 4 people earns between 4 to 5,000, and then you have somebody who earns 100,000. So if you take an average value, because of that outlier of 100,000, it will reflect as if the income per person is higher, but it's not the case. But now if you convert those values to logarithms, so then you wouldn't have such a problem because of such an outlier. And then lastly and most importantly is that when you have logarithmic functional forms, usually you are increasing the normality assumption, which is actually one of the requirements for regression analysis, as well as you are also increasing the homoscedasticity properties, which basically refers to the equal spread of the error of the variance. The variance of the error term. And then, of course, we then know that, it isn't always possible to have logarithmic functional form because sometimes some values cannot be converted to logs, especially maybe if you are dealing with negative values or zero values. Sometimes also if you have values that are already in percentages like inflation rate, interest rate, and so forth, you don't necessarily need to convert them to logarithms. But for example, if you have a combination of variables that are measured differently and some are in percentages, you can then convert the other ones to logarithms so that you can have some form of uniformity in order for you to be able to estimate the regression model. All right. Now moving on. So we have now sort of explain why the logarithmic functional form is important, let us look at the second functional form, which is the quadratic functional form. Now, the quadratic functional form is very important, especially when you are dealing with cross-sectional data, and or mostly also when you are dealing with microeconomic data. So, for example, if we take these wage function where you are estimating here, for example, in this case, we want to determine whether the level of experience or the years of experience do have an effect on your remuneration on the wages. So we estimate this wage function. So you are given the data. So for example, this researcher was given data to estimate, and so this is how the equation came out. And you can see that it's a quadratic form. It is in quadratic format. So now for an equation like this, we cannot just jump on and say, well, experience increased by so much, wage will increase by so much. No, it doesn't work like that. So with a quadratic function, we can actually look at the marginal effect of experience. So in other words, if we want to determine how experience affect your remuneration, we can actually look at the marginal effect of experience. So now what is the marginal effect? The marginal effect is nothing else, but it's basically a measure of the instantaneous effect that a change in a particular explanatory variable, for example, in this case, it's experience, has on the predicted probability of, for example, on wages, when all the other variables, for example, experience squared, are kept fixed. So if we want to, or if we, obviously, if we had other variables, so obviously, if we want to look at the effect of experience on wages, we can only look at it from a perspective of marginal effect, holding all the other variables constant or fixed. So how do we determine that marginal effect? That marginal effect, we basically take a derivative of wage with respect to experience. So obviously we have to use our calculus here. So we can see that experience actually appears in these two expressions. So for example, if we have to take the derivative of wage with respect to experience, we have this value of 0.298 as a derivative of this first expression, then minus, of course, here we have to apply the power rule because here we have experience squared. So then we bring the power here such that we have 2 multiplied by 0.061, which is the coefficient of experience squared. And then, so that will then give us S2 will actually give us the marginal effect of experience with respect of experience on wages. So basically what we can see here is that, for example, if we look at the first year of experience, we can say the first year of experience increases by some, almost $0.3. Okay, and then if we want to look at the second year, we simply follow the same principle, but now we multiply by the number of years. So we substitute experience by the number of years that we want to see. So for the second year, we can then say, okay, that value will be 1. For the third year will be 2, because we start from year 0, 1, 2, and 3. So basically that is how we determine, or that is how we calculate the marginal effect of experience. Now, at the same time, we can also look at the turning point. Okay, why are we interested in a turning point? We are interested in that for a number of reasons. In other words, we want to determine the maximum wage with respect to experience. So this is the formula where we say that formula is, so we denote that by x star or with the asterisk, such that we say, okay, beta 1 divided by obviously 2 beta 2. So, and we know if we go back to that equation, so we have beta 1 is this, so this is your beta 0, this is your beta 1, and this is your beta 2. So we said, so beta 1 divided by beta 2, 2 multiplied by beta 2. So if we go back to just our slide, so we can then basically see that, so that beta 1, so we substitute 0.298 divided by 2 times 0.061, and then it gives us an experience of, that the maximum, wage, in terms of years of experience will be 24.4 years. So what is really a turning point telling us? So the turning point is basically a point of the graph where the graph changes from increasing to decreasing, which is basically rising to fall, or decreasing to increasing, falling to rising. And so basically now what we are saying here, are we saying that the return on experience becomes negative after 24.4 years? Not necessarily, because it will really depend on the number of observations that actually lies to the right hand side of the turnaround point. So it depends on how many observations are here. So obviously if you have fewer observations, then the effect will be different. If you if it's more, again, the resulting effect will be different. So therefore, it doesn't mean that after 24.4 years, then the return on experience will become negative. So that is just a word of caution that I wanted to bring forth. So we can actually look at another example here, and I'm not going to go through it, but I just wanted to highlight one thing. Say, for example, here, if we want to look at the effect of pollution on housing prices, so if we take this variable as what you call it as nitrogen oxide, if as a proxy of pollution, so then we can actually look at the effect of this with respect to that. Okay, and so again you can then calculate your marginal effect. Okay, you can then again calculate your marginal effect, holding all the other variables constant. Okay, don't forget that. And then if you want to look at maybe say in terms of the effect of the room size with vis-a-vis the housing price, again you can basically see, now here I want you to pay attention, look at the difference. Here we have D, because we have D log price over D rooms, you can see here it's a percentage change in price over just a unit, because a room is just measured differently. So that's why you can see that here the denotation is different, because this one is in log form, it's a percentage, and then the other one is just a unit because it's just a room. Okay, it's not logged. So you note this, look at that difference. All right, again, the turnaround point is just the same story, so I don't want to repeat the same thing to bore you. Okay, all right. So of course we can have now other possibilities. Other possibilities we have, you see, for example, here, since the whole equation is log, you can actually see that when it comes to calculating the marginal effect, you can actually see that you have a percentage change in price of a percentage change in NOx, because all the variables are expressed in log form. But if you see in the previous case, price was expressed in log form and NOx was not, the nitric oxide was not expressed in log form. That's why it was just percentage change in price over D NOx. But now because both of them are expressed in percentage forms, so that's why we have a percentage over a percentage, but the rest of the side of the equation remains the same. All right, so and then lastly, we just want to look at the models with interactive terms. Sometimes you can actually see that we have an equation whereby the variables enters the model multiplicatively. So for example, here we are looking at the housing price vis-a-vis the bedrooms and the square feet. So we can actually see that the square footage, we have square footage multiplied by number of bedrooms as a multiplicative expression in that function. So the problem with this is that, of course, now if we have to calculate the marginal effect, we have to take the derivative of price with vis-a-vis the bedrooms. Now, suppose we are only interested in how the number of bedrooms affect the housing price. So now, for beta 2, it's very easy to determine because you only have bedrooms. But now if we look at beta 3, where bedrooms appears again, it becomes a problem because now the effect of the number of bedrooms also depend on the level of square footage, which is a challenge. So, and therefore, models with interactive terms, or interactive terms are basically terms that enters the model multiplicatively, becomes very complicated, or they complicate the interpretations thereof. And so therefore, for one to deal with that, what we have to do is we reparameterize, and whereby we take the mean difference of the two variables that are involved. So if we do that, then we can easily interpret it, and we can also then get the partial effects of the different variables that enters the model multiplicatively. And so that is basically how we deal with models that involves multiplicative expression. So that is the end of the first part, or part one of this lecture. So part two will follow.